last topic here of the big three: center, shape, and spread, before we loop back to the measures of location section, we get to spread. And the first one is there already written in your notes. It's one that you are very familiar with. It's the range difference between the maximum and the minimum. We like to use things that are better than that, though. And if you stop and think about range for just a quick second, I think you can probably figure out why range isn't ideal. And that's because, if you have an outlier, for instance, it's going to really affect things. If you have data values that are really clumped up or really spread out, you don't really get a feel for that by the range. You just get a feel for how far apart two values are. The rest of the values don't matter at all in the range. And so I think it's pretty clear to see why that's a subpar metric. And so we like to use other metrics. The first one that we're going to talk about is standard deviation. A standard deviation is the typical distance that an average data point is away from the mean. And standard deviation is a weird concept. This definition is not one that you're going to find in your textbook, but it is one that I have used because I think it gets to the heart of what it is, because I'd rather you understand what it is than a formal definition that means nothing. So it's a measure of spread. When you hear standard deviation, you're thinking how spread apart are the data values. And when we say standard deviation, we're just saying, okay, how far away is a typical data point from the mean? And it's that simple. When I say that the standard deviation of a data set of heights of trees is 2 feet, then you would say, well, then a typical tree is 2 feet away from the average tree height. If I say that that the standard deviation of human weights is 20 pounds, then I would say, well, a typical human is 20 pounds plus or minus from what average is. Okay, so it's just how far away are things? What's a typical data point? How far away is it from the average? Okay. And then we have a related concept, variance. Variance is a measure of spread that is the square of that. So you need to be able to go back and forth between standard deviation and variance, because whenever I have a standard deviation, I can always square that to get variance. If I have a variance, I can always square root that to get the standard deviation. Variance has a key place in statistics. Basically right at the end of this course. It's not a concept that we're going to talk about very much at all in this course, but if you were to take any other statistics course, variance becomes much more useful. It goes back to the mathematical properties thing we talked about with regards to a mean. We don't use it in this course because if we can choose between the two to use, standard deviation makes a lot more sense. Variance doesn't really have a great meaning. It's a measure of spread, or I think maybe variability. Variance is a measure of variability, how much things vary, how much are things spread apart. Those are all synonymous ideas. But it doesn't have a good meaning that we can put a handle on, where I can with standard deviation. A standard deviation means something. It means how far away is a typical data point. So that's why we like to use standard deviation. It makes more sense, but do be able to go back and forth between them. So example, same data set we had before, but now it says find the standard deviation. And you say, wait a minute, you haven't given us the formula for standard deviation. Some of you have seen this formula before, so you are aware of how to do it. But rather than focus on the formula, I want to walk through the idea of standard deviation and then arrive at a formula, because I'll give you the formula. I'm not going to ask you to memorize it, but I think if we just jump right into the formula, it becomes really easy to not think about what it means, and I want us to think about what it means. So we're going to start off with the definition of a standard deviation, which is the average distance that a typical data point differs from the mean. And we're going to walk through this data set and see, can we do that? Remember, a standard deviation, just like a mean, is a statistic or a parameter, depending on if it comes from the sample or the population. This is obviously a sample setup, so it'd be a sample standard deviation. But a statistic is a numerical calculation. It takes a data set and it boils it down into one number, right? Just like a percentage would or a median would, right? A median would. It boils it down to one number. And so we're saying we've got to combine these 5 numbers into one number that tells me the spread of this distribution. And again, we're going to do that by thinking about the definition of standard deviation, which is the average distance that a typical data point differs from the mean. So just walking through this logically, I'm going to take all my data points and I'm going to say, well, how much do they differ from the mean? If the definition is the average distance a typical data point differs from the mean, first step might be how far are all the points away from the mean? So my first step is going to be list out all the points. There they are, 24, 16, 24, 18, and 13. And I'm going to say, how far away are they from the mean? And so I can fill in this box and say, here's how far away all of those points are from the mean. Now notice I've got a little sum there at the bottom, that Greek sigma meaning sum, because I want to somehow combine all of this into one number. And I have a way to do that because, again, the definition of standard deviation is the average distance a typical data point differs from the mean. So I know at some point I have to average. And I know when I average, what I do is I add up all the data points and then I divide by how many data points we have. So I know where I'm going in this average. I'm going to have to sum all these things up. So I'm going to say, okay, look, I've got to find the average distance a typical data point differs from the mean. I've got the differences. Now let's go ahead and average them and see what happens. And notice, of course, if I add up all those numbers, you get 0. And that's a little bit of a problem. And so how do I fix that? Well, if you'll notice, what's happening is I have some negatives and I have some positives because some of the points are greater than the mean and some of them are less than the mean. And so how do I fix that? Your first thought might be absolute value. If so, that is a great thought. You can do that. There's an absolute deviation. That's a different metric. The downside is the mathematical properties idea. It doesn't work very well at all working with absolute value bars, and so we try a different route. And if you can think of a different way to turn all of your negatives into positives without turning your positives into negatives, that would be squaring the numbers. And so we're going to square all of those numbers. That'll give us all positives, and then we should be able to continue on our merry little way. So notice again, we add up all those values, we get 0. So let's try squaring them. I've squared all of these values, and when I add all of those up, I end up with 96. That's just the sum. I haven't finished this problem off. I still need to do the averaging part. And so you think, okay, let's divide this by 5, but there's a catch. And that catch is with standard deviation. We don't divide by n, we divide by n minus 1. And you say, dividing by n minus 1, that makes no sense. Well, it's a concept that we're going to touch on later in the course. You don't need to know why. So if you just say, I don't really care, it's n minus 1, you're giving me the formula, you can move on with it, that's fine. We don't need to know why. I want to explain it because it may help you put pieces together later. But again, not anything you're going to be tested over. If you think about what is happening here, we are taking a data set and we use that data set to come up with the sample mean 19. Notice that's the one we did earlier in the example. Now we're using the same data set to come up with a measure of spread. We're kind of double dipping. Think about an English class, back when you were in elementary school and the teacher would ask you to define words, and your instinct was oftentimes probably to try to use that word in its definition. It probably came up at some point and your teacher said, you can't do that. You can't use its own word in its definition. And that's kind of what's happening here. We're using the data set to find a mean, and then we're using the data set to find a spread, and that's double dipping, and we can't do that. And so we have to kind of take a little bit of a penalty. We have to make an adjustment, maybe is a good way to think about it. And so instead of dividing by n, we're going to divide it by n minus 1, okay? So we're going to take this 96, we're going to divide it by 4, because that's n minus 1, right? N is 5. So we're going to divide by 4, not by 5, except here's the catch, is that if you trace through the units of this, we have a bit of a problem. Notice these are in home runs. When we take home runs and subtract home runs, we get home runs, right? This dude hit 24 home runs, and the average was 19 home runs. So 24 minus 19 is 5 home runs, right? If home runs doesn't make sense, like apples, right? You have 24 apples, you have 19 apples, you lose 19 apples. Now you get 5 apples, right? When you square, you have to square the units as well. So this right here is 25 home runs squared. Then when I add up a bunch of home runs squared, I'm still in home runs squared. And then I divide by just 4, I'm still in home runs squared. Well, what's a home run squared? Or what's an apple squared, right? None of that makes any sense. And so this is that idea between standard deviation and variance, is when I square root the variance to get back to standard deviation, now my units make sense. So I'm going to go through all this work of subtracting these values to find the differences, squaring them, adding them up, divide by n minus 1, in this case 4, and then I have to square root to get to standard deviation because that's the units that make sense. 96 divided by 4 would be the variance. And again, variance doesn't have a lot of use for us. It doesn't mean anything, but then when we square root, we make those units make sense, and now we can say how far away the typical player was from the average player. And so I'm going to finish this problem off by saying, here is our formula. We'll write it down on the next page. 96 divided by 4 is 24. Take the square root, and that is 4.9. And our units now are in home runs, as opposed to the variance, which would be home runs squared, which again doesn't make any sense. So the sample standard deviation, our symbol S, is defined as the square root of, and again, this is a complicated formula if you haven't seen it before, which is why I wanted to walk you through the example. Hopefully it makes sense based off the example, is that we are going to take all of the individual values and subtract the mean. Then we're going to square all of those values. Then we do the summation. Remember the Greek capital sigma here means sum. So then we add them all up. Then we divide by n minus 1, and then we take the square root, little order of operations there to finish this off. We have a population standard deviation. It has a symbol, as we mentioned earlier. It's going to have a Greek letter. This is a lowercase sigma. So our sample standard deviation is symbol S. Our population standard deviation is a lowercase Greek sigma. And it's found in a similar fashion, except here we have a sample standard deviation, so we have to subtract a sample mean. We're in the sample world over here. Here we're in a population world, which is why we have mu. And now we have capital. And you say, well, where'd the minus 1 go? It's going to kind of come back later why that went away. If we're in the population world, there's really no penalty to take because we are using everything we have anyway. Again, not something really to stress on, but it will be something that comes back up later. And I'm going to link back to this and hopefully you go, oh, okay, that makes sense. For now, if it's a little fuzzy, that's not the end of the world. Again, I'll provide the formulas with you. The main concept that I want you to get is that standard deviation is how far away is a typical data point. It's not a scary thing. It's just how far away is a typical data point from the mean. Lowercase s is going to be our symbol for sample standard deviation, and then that lowercase sigma, that Greek letter there, is going to be our symbol for the population standard deviation. When we talk about variance, the formula is going to be the same, except we just don't square root. Remember when we worked through that example, we said if we had stopped before we square rooted, that was the variance. So our sample variance is going to look the exact same, just no square root, but our symbol, we don't have to come up with a new symbol. We just say s squared, right? We get to cheat a little bit there. So instead of having to come up with a whole new symbol, we just have s as our symbol for standard deviation, s squared our symbol for the sample variance. And that should help you keep them straight because we know that variance always has units that are squared, and it's always going to be a number that is the standard deviation squared. And then similarly for population variance, but I don't really care about the formula because we'll never talk about this formula. Just note that it is sigma squared. Let's go ahead and just have you these steps for to calculate that, because you might be like, man, that was kind of crazy how we calculated that. Just have a place where you can write them all down. Just go in order of how do I actually calculate this thing. Here are the steps. Again, it's going to be just what we did and just having you write it down formally. Number 1, calculate the sample mean x bar. To get the sample standard deviation, we have to get the sample mean. That was that 19 value. We had done that previously in these notes, so that's why we didn't have to do it again there. And then because, again, the definition of a sample standard deviation is how far away is, a typical data point from the mean, we had to say, well, how far away are the data points from the mean? So that's where we subtracted all of the individual data, or the mean from all the individual data values. So for each observation, calculate the difference between the data value and the mean. Then we took those differences and squared them. Then we took those squared values. Remember, we did try to add up the unsquared values. That didn't work. That's why we squared them. Then we got to add them up. So step 4 is to sum up all those squared differences. And because, again, our definition was how, what's the average distance a typical data point is from the mean. This is that average part. We had to add up all those values, except we didn't divide by n. We divided by n minus 1. If we leave it there, that's the variance. And then to take the square root, that gets us to standard deviation.